everyone. It's a pleasure to have you all here for another exciting edition of Stories Behind Products. I am thrilled to share with you the latest developments in marine conservation. Let's dive right in. Did you know that keeping the hull of boats clean can have a positive impact on the environment? Preventing biofouling reduces CO2 emissions and enhances the performance of boats. It also helps stop the spread of invasive species between ports and decreases the amount of toxic anti-fouling paint that harm marine life. I'm Oya Demirbilek, a professor of industrial design at UNSW, and I'm delighted to welcome you all from the beautiful Bijikal country. I pay my respects to the Bijikal people, who are the traditional custodians of this unceded land, and I acknowledge their elders, both past and present. So we are lucky to have Tom Loefler, CEO and co-founder at Hullbot, as our presenter today. Tom is an inventor, industrial designer, and innovator, passionate about using robots to improve ocean health. Tom is a true expert in his field, with experience in developing product concepts and prototypes across multitude of industries, including transportation, medical devices, scientific equipment, architecture, and consumer products. Tom will discuss Hullbot, a state-of-the-art underwater drone platform capable of inspecting, mapping, and interacting with submerged structures. And Hullbot is tackling one of the most difficult challenges in mobile robotics using machine learning and low-cost cameras. And Hullbot has received numerous awards, including the Ocean Changemakers Award, the Ocean Impact Organization runner-up, the New South Wales Climate Spotlight Award, the New South Wales Ocean Innovation Award, and the Top 10 Biofouling Innovators Award, among others. You can ask questions via the chat function. And now it's time for Tom to take the stage. Over to you, Tom. Over to you, Tom.
Thank you, Oya. Fantastic to be here, seeing some familiar faces from a few years ago now, and looking forward to taking the rest of you through our journey and using it as an opportunity to spread a bit of excitement about the power of design and the power of innovation to have a positive impact. So let's dive right in. So a lot of you will be interested to know how we started doing Hullbot and why I started working on Hullbot in the first place. So I'm an industrial designer, like most of you on the call, and I think it's an interesting point of discussion to place robot within the kind of timeline of industrial design, you know, which has been dominated recently by apps and other digital technologies. But if you take something like the appliance when it first came out, there's a radio on the far left. And no one had any idea what something like that should look like, right? It looks like a piece of furniture with some electronics inside. Then we've got the inimitable Dita Rams there, of course, the iPod. Then we sort of lost our way and let the people making apps and internet products have all the fun. And as far as I can see it, the most exciting and most interesting possible products that can have the most impact are robots. And so, you know, we got into this mess in the first place because I'm personally very fascinated by the opportunity to bring industrial design to a field that's been very engineering and sort of hard technical skills focused. And what could we do with fresh thinking and, you know, sketching amazing robots for, you know, a utopian vision there. I'm not sure whether drones should milk sheep, but that seems to be what's happening there. But that kind of thinking is where Hullbot came from. So I'm going to go through the design process a little bit in a second, but I thought I'd just start by talking about biofouling, which I'm very passionate about, and is quite literally the biggest environmental problem that many people have never heard about. So biofouling is the growth of marine organisms on the hulls of submerged vessels or structures and it has serious implications for our planet. So there are three interrelated problems with biofouling. The first is that stuff grows on hulls and it makes them harder to push through the water, meaning that boats and ships use more fuel. And it is at least, but we say approximately 1% of global greenhouse gas emissions are caused by fouling on vessel hulls. So it's a very, very big problem that we're tackling here. The main way that boats have been kept free from stuff growing on their hulls, or the best we could do for a long time, was to paint the hulls with anything we could find that would kill stuff that was on or near the boat. Boats used to be sheeted in lead, they were sheeted in copper, arsenic, cyanide, and for 2,000 years, we've been putting anything poisonous we can find into coatings on the hulls of boats that can release those toxic biocides into the water. And of course, what do we mean by that? We mean paint, which is for the most part plastic, liquid plastic that dries or partially dries on the hull with poison in it. And that is what anti-fouling is, and it is on literally every hull in the world. And as that paint releases its biocides, which are harmful to marine life and accumulate through the environment, the plastic itself also comes off, and it's the largest direct source of marine microplastic pollution. But like I said, it's a wicked problem. You can't just ban anti-fouling paint because boats will look like the image on the right there almost straight away, leading to massive increases in emissions. So you also have the third issue, which is invasive marine species. You know, boats get stuff growing on them and they move from place to place, and the stuff comes off and the organisms spread through new environments and can be very disruptive. And nearly 80% of invasive aquatic species transfer is from biofouling on hulls. So this is a big and complex issue, and we believe robots have a significant role to play in this. So how quickly does this problem happen? Well, biofouling grows in hours and days, and the light slime, which can develop in days and into heavy slime sometimes in weeks, has a disproportionate impact on the emissions from that fouled vessel. And so you can see that even having a deteriorated coating or light slime with only 0.5 millimeters of a biofilm, so you wouldn't be able to see it. You could feel it with your hand, but you wouldn't be able to see it, is already causing a very significant impact on the efficiency of the boat through the water and therefore the fuel that it uses. And the light slime becomes the layer for heavy slime and then shells and weed. And by the time you have some barnacles on there, you're already looking at a very significant increase in the drag. Anti-fouling paint, like we said, it's an extremely harmful. It's poison that is painted onto a boat to kill stuff that's near the boat. And they're being banned in some areas, but there isn't a good alternative. Like I said, it is a wicked problem. Very expensive and costly to lift vessels out of the water and repaint them. And the paint don't prevent slime from growing. So the majority of boats are cleaned by divers regularly throughout the 1-year anti-fouling cycle. And then they are lifted out, stripped back, repainted, put back in, only to be fouled again, and then cleaned by divers and polluting the ocean the whole time. So to give you a sense of what we're talking about here, this is a video that we've made recently as part of an outreach to some of our partners in the US, this is a flyover of San Diego, and you can see the number of boats in the world that are affected by this issue. All of these vessels are lifted out, painted, put back in, usually annually. But being California and being quite progressive, they have actually banned toxic anti-fouling for recreational boats. And there's just not enough divers to clean all these boats. And certainly divers can't come often enough or safely or do any of the things that a robot can do. So a big problem that we're tackling. So our solution, and this is a image of our 5th generation Hullbot. So, and we're currently on our 6th. Yeah, our solution is to use a robot to do frequent cleaning that will remove early stage slime without the need for the toxic paint and without the need for divers. So essentially putting a robot in the water to remove the slime and make the whole problem go away. So quite a radical concept, and in other ways, quite a simple concept, but we'll get into how complex the technology is that does this in a little bit. So how did we start? Well, the first thing we started with was, of course, research and interviewing customers and industry. And I think there's quite a few designers early in their career on the call. So I think it's very, very important to recognize that we didn't start with a cool idea of a robot. We started with a lot of research and interviewing as many customers as possible and learning as much as we could before starting with the solution. And then I started sketching. So here you can see some of my concept sketches from the early days, thinking about what would a robot look like, how would it move, how would it clean, how would it find its way around, would it float on the surface and have kind of cleaning appendages, would it swim like a seal through the water, sort of torpedo-shaped structure, would it spin like a lantern, cleaning as it went. And it's very important to take after doing the research and understanding how people currently do it and what they think is reasonable and sensible, to take an imaginative and first principles approach. And I certainly enjoyed doing that, and I miss having the time to do sketches like this. So it's a big part of my process still today, but yeah, definitely good to remember where it came from. Of course, Hullbot was a major project at UNSW. So here you can see the SolidWorks on the left. And I've got a tip for anyone who's currently still studying, which is don't make your appearance model a functional underwater robot. It's very, very hard, and it takes a lot of time out of producing your design communication materials. Now, I'll be honest, it certainly didn't work for the presentation, but it did work subsequently, and we were able to deploy it and with some friends make some videos of it and use that to get going. So there's definitely a lot of value in a proof of concept prototype, but it's a lot of work. So just, yeah, do one or the other, but don't make them in the same object would be my advice. So here's Hullbot as the working prototype. On the top left, you can see it spinning its brushes and sticking to a hull and cleaning slime off the antifoul. And on the right, you can see the robot. It has molded polyurethane brushes made from 3D printed positives. The thrusters are made from PVC pipe from Bunnings and hobby motors and RC boat propellers. And that tail coming down the bottom actually has 3 servo motors in it and was able to fully articulate to steer the robot through the water. We had a lot of fun. Subsequent to that, I founded a startup with my co-founder, Carl Watfern, and we built an entirely new robot with different materials and a different design. That's the 2 of us there in the garage on the left, building H2. It had a very different design with rotating abrasive sponges, 5 thrusters, and a whole bunch of onboard electronics and batteries that enabled it to swim around underwater and clean things off. And it cleaned a lot better than the first one. And with that, we were able to raise our first angel investment and build a bit of a team. There's quite a long story in between, but I'll just jump through to where we are today. So we're now a team of 22 based at the Sydney Super Yacht Marina. We have a fully equipped workshop there with everything from a test tank inside the office to a boat outside with plenty of power and 5G router and stuff installed in it for robot missions out on the harbour, a trailer to take it further away when we need to, and obviously a big electronics lab, big workshop, a whole range of other equipment. And about half the team these days are mechatronics and software engineers who focus on all the things that are inside the robot and make it do its thing. So about 18 months ago, we raised seed capital from a mixture of Australian and US-based VC firms and angel investors and so on. And that, along with some grant money, enabled us to deploy a fleet of 10 of these robots to clean boats for customers all over Sydney Harbour. That taught us a lot about how customers react to the product, what they like and don't like, how to take their money, how to keep them happy, how to operate a fleet of robots, which is very, very different to building and deploying one, and how to do all of that in innovative ways with relatively little capital. And along that journey, we discovered a lot, and so we've built an entirely new robot. But to give you a sense of how the previous one worked, so original product concept, still alive and well, is to have autonomous hull cleaning for every vessel. In the long run, it makes sense to just have one robot at every boat, so it can clean it a little bit every day and solve all the problems of biofouling. Currently, we use each robot to clean many different boats under a subscription cleaning service. So we have 2 parts to our system. The robot, which is currently there cleaning a boat hull using its cameras to find out where it is and where it needs to go, and executing a kind of rectangular cleaning patch on the keel of this boat. And then the other part is the pod, which retracts, stores, and recharges the robot, making it into a fully self-contained system. So essentially we have a robot and pod system. The pods put the robots in and out of the water via their tether, provide power and data, and are connected over the internet, so we can operate pods remotely. And we can leave a number of these in a marina. And if someone on site is kind enough to move them between berths, we can keep a marina full of boats clean. In terms of the robot, it's a free swimming robot that can move in all directions in the water column to approach and inspect and map and clean different structures from different angles. And it's able to pull back and get situational awareness again using its cameras and do an analysis of how well it cleaned an area and then move back in and do that next patch, which would not be possible if it was a crawler and say stuck on with big suction system and drove around with wheels. So, and then in terms of cleaning, because we're targeting cleaning early and often, we don't need to remove shells, and therefore we can use soft cleaning brushes, making for a much smaller, much less energy intensive, and ultimately much better approach to this problem. So we don't damage coatings, we don't damage the paint, even if the boat has toxic anti-fouling paint, which unfortunately most or almost all boats do. We can clean the slime off the top of them. So in terms of a business model, the robot and pod create a small portable system that can be installed on a boat, installed on a berth, or moved between different locations. Can be easily stashed somewhere when you're doing a passage or during racing or something like that, and then mounted back on the side of a boat to get the job done. And then our team can connect to the system over the internet. They are autonomous for the most part, but we keep an eye on them. Our goal with the latest robots is to have one operator able to watch 3 robots that are cleaning simultaneously and many more that are in standby. So from a small number of people, we can operate a very large number of robots that can then service an even larger number of customers. The way we monetize this is as a subscription cleaning service. We offer regular hull cleans to boat owners, so they don't do anything, they just pay us every month and get a clean hull. Depending on the vessel, they pay that monthly subscription for daily, weekly, or fortnightly cleans. We encourage them to do it more often. And we send them a nice report with all kinds of scientific information about the status of the hull and what interesting critters we found on there, and videos of the robot, and use that to communicate our mission and our impact. At the moment, we're focused on rolling this out through marinas, trying to put multiple Hullbot One systems in each marina. We'll own and manage the hardware. The marina employees will move them between boats, and then we'll get all sorts of amazing data and insight monitoring them over the internet. So it's quite revolutionary. We're offering people a clean hull always, not just cleaning after it's fouled, but keeping it clean the whole time. That'll ultimately be cheaper than any other approach. It'll have the least drag of any anti-fouling approach, making the boats faster and use less fuel, and it'll be the most sustainable, ending the reliance on paints and stopping the spread of invasive species. So in terms of process, I think it might be obvious, but also non-obvious how difficult underwater robotics is from an innovation standpoint. And you know, it's obviously that it's a technical challenge, but one of the things that as designers we're very familiar with is iteration and trying to make and test and in an agile way, you know, explore and do things again. But that's easy to do with certain things. It's very hard to do with underwater electronics, because the stuff gets wet and then you can't put an oscilloscope or a multimeter or measure it or do anything else, because you've got to like dry it and open it up and do all these different things. So it's hard to be nimble and agile. Importantly, there's limited sensing. So for a robot to do something useful, it needs to know something about its environment and then plan an action based on that, and then give a command to its motors and other actuators to go and do something. And so for a drone, it can use its GPS to know where it is. And you can do things like waypointing or come back to base or things like that. Underwater, you don't have technologies like that. So you don't have GPS or radar or LiDAR or any wireless communication. Sonar, if you've ever used a fish finder or been on a boat with a fish finder, you'll see that there's really very little information coming back to you. And then the third challenge is everything moves. So if you're building a warehouse robot and you cut power to the motors for a second, it'll stay right where it is, as will the building and all the shelves and all the boxes on it. And there isn't kind of a maelstrom of different particulates and lighting effects moving in every direction. So it makes it quite a challenging environment to innovate within. And yet, in focusing on cleaning the hulls of boats, which might seem like a simple problem, we've now developed innovation and novel IP across the full stack of an underwater robotics platform, which is why we proudly state that we are building the world's most sophisticated underwater drone, because in solving for cleaning, it gives us a multi-purpose platform that can inspect, map, and interact. And the things that enable it to do that go all the way down into the sensors we build, the motors we build, the way we arrange them, and the whole holistic structure of the robot is a very tightly integrated and iterative conversation between industrial design and the other engineering disciplines, science, customers, experience in the field, data that we get back, and so on. And so we have solved some really interesting and unsolved problems in a new way. So the Hullbot One System, which is our latest robot and pod, we've focused on 3 key areas: the camera-based autonomy, which is the core technology that makes all this possible. We've put that into a multi-purpose platform, which is able to move the brushes around from place to place or anything else that you'd like. So there's a payload bay at the front and a payload bay at the back, and a whole range of different sensors and so on. And then, of course, the pod, which puts it in and out of the water, but also gives us a system that is capable of remote, unattended operation over days, weeks, and months, which is pretty important if you want to clean every day, but also very important if you want to do something of higher value in a remote place, or be able to put a robot in without sending a ship and a whole bunch of experts to a location. You can just have a Hullbot system somewhere on board and get the mission done. So this tech stack and this product will be the same across a wide variety of different opportunities. Like we mentioned, the problem of invasive species. We've all been through customs and seen how careful we are to not bring any biological material in, but there are 60,000 large vessels entering Australian waters covered in growth like this, and at the moment there is no solution to inspect them or monitor them or clean them, and we believe we have the solution to that. Aquaculture is obviously very important for feeding a growing population. But when you put fish and fish feed into a net, it is the ideal environment to grow biofouling rapidly. And again, one robot per net will solve the problem. And again, with offshore wind, all the mooring chains, all the structures, they need cleaning and inspection to maintain that asset risk. Otherwise, you're sending a ship with divers out to each one regularly, which will eat into your carbon impact pretty quickly. So I want to give a huge and important shout out here to our amazing engineers, and there's some of our software team looking down into top camera of one of the robots, but they really make all this possible. Doing things like the machine learning you see in the middle, that's part of our work, is using the robot to help manage the overabundance of sea urchins, which are eating all the kelp in Tasmania and Victoria and wreaking havoc on already stressed ecosystems. So the robots are able to detect the sea urchins, and obviously we can do mapping and data, and we can also kill them with Hullbot, but that's the story for another day and maybe a bit gruesome for this presentation. So on a more positive note, we also use the robot to do a variety of direct science and research missions around the impact of mooring chains on seagrass meadows. Seagrass meadows sequester 35 times as much carbon per square meter as tropical rainforests. So it's important to preserve them and not drag chains through them constantly. So we're active in areas like that. And I'm sure you have lots of questions, but here's an image of one of our Hullbots scrubbing fouling off a vessel over at Manly a couple of years ago, and you can see that it does clean boats. So love to answer any questions. Oya, do I just jump into the chat and
Tom, I will read you the questions because the audience cannot reach directly to you. So we have a few questions that already came. Thank you so much for this lovely story so far and how the product has evolved. The first question comes from Damla Hatipoğlu. She's asking about the process. She says, what was the process of figuring out how to teach the robot to do what they wanted to do? So how did you teach Hullbot to clean the hull?
Yeah, it's a great question. So there are many different pieces of software that run on the robot, from systems which just monitor all the systems on the robot to systems which make it easier to send commands to other parts of it, to image processing pipelines that take in video feed and try and turn it into information. So it's quite a big topic, but we certainly discovered a much more challenging problem than we thought with each new generation of the robot. And we learned different things. So I'm not sure whether I've answered your question, but it's very complex and I don't want to give too much away. So
that's understandable. Thank you, Tom. Daniela, do you want to ask your question?
Sure, thank you. So I was really fascinated to hear how difficult it has been to design for that underwater environment. And you mentioned that you had 6 versions of the robot, I think, to date. And I was wondering if you could tell us a little bit about how long and what kind of development kind of occurs between each version of that robot. Like, is it a couple of months, a couple of years? Yeah.
Yeah. Okay, so the first thing to say about that is we've become very good at making the robot from a system of as an assemblage of modules. So for example, a robot has 8 identical thrusters, 4 identical cleaning motors, 4 identical daisy chains of light, you know, a number of identical cameras and other things like that. And so that enables us to both build them and maintain them efficiently, but also to make improvements on those modules within the constraints of the boundary drawn around that module. And so with the latest robot, we spent a significant proportion of our design time thinking about what we might need to change or what we might want to improve, and making sure that the description of the interfaces and the interaction between that module boundary were clear and cleverly drawn and distinct, so that sub teams and or individuals could improve a sub module without kind of getting trapped within the overall architecture of the product. And that's quite hard if you don't know what the finished thing's going to look like and you're already trying to chop it up into different sections. And remember that this is across mechanical, electrical, and software, and that the module is part of a multi-layered process. Within each generation, there are many iterations of the robot and the modules and the sub-modules, and of course the software, but you can't change everything. And we think that the kind of main structural elements are pretty stable now. And we've learned to make anything that we're not, or where we think there's a big opportunity for improvement, either in cost or performance or capability, wrapped up within a neat module so that we can change it. So for example, our latest robots have 6 perception cameras, which are connected through to the central sort of motherboard, if you like. And that motherboard has a daughter board, which has our circuits for processing those cameras as fast as possible, which we actively work on kind of separated out so that we can improve portions of the robot's behavior or modify it between different use cases, or as the code gets faster or new chips come out, without needing to go to Gen 7, if that makes sense. The same with things that need to be replaced or serviced. And it also unlocks really interesting opportunities in terms of designing in high volume production, because for 100 robots, we need 800 thrusters, but with spares and different versions, we're currently building them in waves of 250. So they can improve and be made cheaper and more reliable and faster and use less energy and whatever else, provided they fit within the same location and plug in with the same plug and talk the same language. So it's taken a while to learn how to do that, and that's very unusual in underwater robotics, where traditionally robots are made by assembling off-the-shelf thrusters, say, into a frame for one specific job. Yeah.
Thanks, Tom. So the next question is from Ethan Brown, and Ethan says, I always find it interesting when nature is adapted to design. So when developing the geometry of the sponge pads, did you reference naturally occurring predators, such as the geometry on the mouth of marine snails, which typically consume diatoms, or was there another method used to develop the final pad geometry, which proved more effective for cleaning diatoms?
That's a fascinating insight. The brushes are another example where we tried a variety of different materials and a variety of different shapes pretty quickly, mounted onto the same kind of central part. To be totally honest, the cleaning has taken relatively little of our attention. The sensing and the control and how it moves around the boat has taken a lot more of our attention. So we think that there's a great opportunity to do more bio-inspired design and biomimetic design for the cleaning brushes. And I'm going to look into this snail. It sounds interesting.
And the next one is a comment that says amazing, from Mark Bertinetti, and he says amazing work to productize and protect the IP from a project from university. Really impressive work, he says. The next question is from Jack Smith, and he says, for commercially large vessels such as container ships, would the Hullbot be scaled, or would there be multiple use on the one ship? Multiple of them on the one ship?
Yep. The short answer is a bit of A, a bit of B. Project Big Bot. If there's any branding people in the house and you want to give us a hand on coming up with something better, we're all ears. No, frankly, the same cameras and code and into a slightly larger robot that can handle more waves and more currents will get us inspection and cleaning of larger vessels without much change to the overall design. The area we're most interested in with the current size of the robot is propeller polishing. There's a small area of the ship, but a very large impact on it. Fuel consumption comes from any growth on that propeller. And of course, it's great at inspecting large ships when they're in protected waters. So we fully intend to address that market, but we humbly concede that we have our hands full with the 35 million vessels that are in the under 300 meter category. So we've got plenty of boats to keep busy with.
The next question is from Mark Bertinetti, and he says, how does this compare cost-wise to having inflatable dry storage that lifts the boats out of the water? I've only seen these for speedboats, not yachts.
Yep. There's a great product out there called FabDock, which basically looks like a rubber ducky that you drive the boat inside, and then it closes up and pumps the water out. It's a great solution. It requires the boat being within a marina with less than 30 centimeters of waves. So you need a marina berth and a FabDock. And as you can imagine, one of the challenges with boats is they're all different, which means each FabDock is custom made to the vessel outside of a number of commonly sized smaller ones. It does solve some of the problems. It doesn't actually clean the vessel, so it will progressively get dirtier and stay dirtier whilst it's in the FabDock. But the FabDock then gets fouled, which means you need to take the boat out and then take the FabDock out and clean the FabDock, or unfortunately, in many cases, throw the FabDock away because you can't really clean stuff off an inflatable very well that's been in the water for 5 years. So but we're very supportive of anyone doing something other than putting toxic paint in the water by 10 liters a year for a small boat and thousands for a big boat. It's got to be a better way.
Right answer. The next question is from Luca Harriman, and he says, love the idea of the hull boat, Tom. As graduate of the honors program, were you working elsewhere whilst still developing the Hullbot? Is his first question.
Yes, I had to have income for a while there. So I did work elsewhere. I was lucky enough to work with an industrial designer when I was an undergraduate, which I highly recommend to people. And I learned a lot there. I also ran my own freelancer business doing mostly hands-on work, but some design work, particularly with architects and shop fit outs and custom furniture and things like that. Yeah.
And his second question is, what were some of the biggest challenges with getting this product off the ground and having your market use your product?
So there's sort of one school of thought with startups and new products is you make something simple and you get it to market quickly and survive from the revenue that you can get. And if possible, you can do crowdfunding and Kickstarter and things like that. That model is hard to do with a fully autonomous underwater hull cleaning robot. So the challenge for us was convincing investors and securing government grants to give us the capital we needed to build a team, establish a workshop, and build and deploy robots to learn how to make better robots and then better robots again, and repeating that process to get to where we are today. It's a lot of work, it's a lot of determination and dedication to get there. Startups are a really interesting place, and if anyone's interested and wants to reach out and ask questions about that separately, I'd be happy to give advice. It took us a while to meet the right people within that community, and now we have a strong network and are able to get introductions quite easily to venture capital funds in Australia, the US, and Europe, where we're able to get more money. But definitely that's been the hardest part, other than, of course, all the CAD and electronics design and all the other things that we've done. Yeah.
Long hours of work. The next question is from Josh Flowers, and he says, an awesome product, Tom, congrats. What software are you using for controlling the low levels robotics? Something like ROS?
Yep. We used ROS1 as the operating system, and then a mixture of Python and C++ with a fully Dockerized and containerized environment. We've sort of exhausted all the literature and open source projects out there because we've broken new ground. So the majority of our important software is all written in-house. But we did use a lot of open source code early on, including a big project called ArduSub, which is forked from ArduPilot, which is a big open source drone framework. And that certainly helped us in the first number of robot designs to get the thing moving around and controlling the low-level actuators and taking in information from the basic sensors. But at the level of agility and dynamics and so on that we're facing now, it's entirely custom.
Next question from Miles Park. How do you capture emerging tech into your product development, given that huge tech companies dominate, example, artificial intelligence, battery tech, edge computing?
Yep. So we have a good relationship with NVIDIA, who provide, a number of really amazing small form factor embedded systems for edge compute and edge AI applications. We have 3 seats of Altium and 3 PCB design engineers. So we're able to build the robot and build all the circuit boards and select the components, the chips that are in there. And so our mechanical CAD happens on Onshape, but in a very tight loop with Altium and the electrical engineers and in discussions with software engineers. We did face some issues during the chip shortage, which some of you might remember from, it's sort of still ongoing, but it was really bad a while ago, where we were redesigning perfectly functional parts of the robot just because we couldn't get the components. And in some cases had to do that a couple of times. It is a rapidly evolving space. I will say that an area where it's not evolving nearly quickly enough is underwater, maybe because of the challenges I mentioned earlier. And so one of the things we're quite good at, Miles, is taking stuff that's cutting edge in drones or cutting edge in ground vehicles and using our ability to prototype and iterate quickly to shoehorn those sensors or chips into our products and leverage them to achieve our objective without maybe running through the whole process and rigmarole that a larger company or a big defense prime or a company working with, say, the oil and gas industry would take a much more measured and slower approach. We can buy things and try things very, very quickly. Yeah, it's a super exciting time to be building complex products that have hardware, software, a service layer, and data all vertically integrated. And yeah, robots of the future.
The next question is from Mauxignon, and he says, "Hi Tom, thanks for sharing. I want to ask, how do you clean the soft brushes on the Hullbot, and how often do you need to clean it?"
Yeah, so we don't need to clean the brushes, and that's actually an important part of their design. So they're able to clean just from the agitation of the water as they spin through. And so we never need to clean the brushes. We've cleaned with abrasive sponges and with bristles and things like that, and they tend to get filled with fouling, and not only does it look terrible, but they smell terrible, and then the robot reeks, and it's much better to have the brushes clean themselves. So yeah, not a problem we face actually.
And the last question from Honor, he says, "Thanks a lot for the presentation and congrats to you and your team for the successful product. I want to learn a bit in detail about how did you manage to handle the second nuisance that everything moves underwater and the angle of propellers are unusual than regular." He means unusual, I guess. Are they designed that way to apply more force in surface for the cleaning job?
So how do we deal with everything moving?
Guess so.
Is the first question. We do a very advanced sensor fusion where we predict the motion we expect to have had over a period of time of the robot, as well as the motion of objects in its environment, and the water around the robot and try and solve an estimate of what must have happened and where the robot must be. In some contexts, it's really amazing that the robot's able to find any information from the noise, because at the surface, it'll be incredibly bright. Under the boat, it's pitch black. You have ripples and bubbles and all kinds of distorted, reflected and diffracted light moving everywhere, small particulates moving everywhere. The boat's pretty featureless. So yeah, it's a very challenging problem. It's very, very different than using cameras for computer vision in the air, where you can see a long way without any disturbances. So it's a very complicated mathematics, and we have an amazing software team that are really expert at solving that problem. In terms of the control side, we have mapped all of we have a kind of a physical model of the robot, and we know how each thruster will move the robot around. And so we're able to give very precise instructions to each of them, and the arrangement gives us full 6 degrees of freedom operation through the water. So X, Y, Z, roll, pitch, and yaw. We can move across any of those vectors at different speeds. And so, yeah, combining sensing the environment through to actuating is core to robotics, and very challenging to do in this domain. And that whole problem is contained within trying to clean the hull of boats that are moving around in water that's moving around with a robot that's moving around. Yeah, we've nailed that, and now we're focused on doing it for lots of boats in a way that can not only break even, but scale and have a massive impact on the wider industry.
And I think Onor's second question is about the angle of the brushes. Yeah. And he says, are they designed that way to apply more forces on the surface for the cleaning job?
The brushes on H5 look very different from the brushes on H6 and so on. So we have changed the style a little bit. They do a good job of protecting the boat from the robot and the robot from the boat, because they kind of cover all of the top and the side and the front and the back. They clean quite well. They're not designed to apply more force. They're designed to conform to a variety of different shapes, because the boat has a lot of different curved and strangely shaped areas. And those brushes are rubbery, and they're able to bend and twist and deform and clean slime out of tricky places.
Fantastic. So that's all our questions. Thank you, Tom, for your fantastic presentation and for sharing your story with us. It was a pleasure to have you here today. And also, I would like to express my gratitude to everyone who attended this evening, making it even more unforgettable. But I have also to share the news of the next talk. So I want to announce that our next edition of Stories Behind Products will take place on April 10th. Alfred Boyakis and Julian Chow from the UNSW Industrial Design, they graduated a while ago, will be the next presenters, and with the story of Foresight helmets. So stay tuned for the invitations to this event, and we look forward to seeing you again for the following Stories Behind Products. Stay safe and well, and until then, goodbye. And Tom, thanks again. Heaps.
Thank you. Thanks, everybody.